Hello and welcome to episode 2 of CS350 Online. I'm your host as always, Leslie, and on today's episode we are going to start our discussion of threads. Now for those of you who are wondering why are we starting a little bit late, it's kind of ironic, but the OS instructor got screwed over by a Windows update and getting logged out of my Twitch account. Alright, so today's episode is going to start the meat and potatoes of the course. But before we actually get into that, what I'd like to do is actually start by talking about the OS of the day. So let's move over to that. Our OS of the day, the whole point of this is to try to introduce some of the history of operating systems into the course so you can kind of see where have we come from to know why we are where we are today. Now, I'm not going to start at the earliest operating system because there's not much out there about it, but I am going to cover some of the operating systems which have in history been important for one reason or another. So the first one I want to talk about is a bit of a mouthful, and that's GMNAAIO. Now, this was released in 1956, and it was released for the computer known as the IBM 704, which was a fairly popular mainframe machine at the time. And the photo you see here is actually a picture of the 704. Now, as the name of this OS would imply, it's a joint development between General Motors and the North American Aviation Association. Now, this operating system, because it's from the 50s, it isn't like any traditional operating system of today. This operating system was an I/O library, as its name would suggest, as many of the first operating systems were. And the whole point of being an I/O library was simply because you wanted to make sure that you had abstracted those elements of program design from your developers. So you're offering them a consistent way to interact with the different I/O devices that the computer might have. And that's going to be less of a burden on the developer, and it's also going to guarantee that things actually work as expected. The other thing that this operating system was known as a resident monitor and a batch processor. Now, what a batch processor is, if you've ever worked with Windows batch scripts, is you can kind of give it a sequence of things to do, like run this program and then run that program. And when you're done that, run this next program. So it's a sequential list of programs, and you're just going to, when one program runs and completes, you choose the next one from the list. Now, the resident monitor is what is going to happen in between the switches between those jobs. So this is a very basic operating system. And if you're curious the kinds of programs that might have run on this, you're looking at things like simulations, inventories, payrolls, things like that. And my understanding is about 40 systems around the world were actually running this operating system. And in 1956, that's actually quite an accomplishment. All right. So in our last episode, we were talking about all that boring administrative stuff. We don't need to review that. But we were also talking about what an operating system is. Now, remember that an operating system is kind of a collection of programs and utilities, including a kernel that's going to create the execution environment for a program. It loads the program, and it manages and abstracts hardware and software resources. It handles events. So operating systems do lots of different things, and again, depending on what era you're speaking of, what an OS is and what it does will change. We're going to keep discussing things from a modern perspective, though. Now, we'll leave that there, and I'd like to now talk about our new topic. So we have a bit of a chicken and an egg problem. If you look at a lot of operating systems courses, and one of the interesting things about an online term is that you could go to another school and you could watch their OS lectures. It's totally up to you. A lot of different OS courses, though, they cover not threads first, but processes first. And the thing is, you can't really talk about threads without talking about processes, and it's hard to talk about processes without introducing the concept of threads. Now, years ago, concurrency, that's 343, actually used to be the prerequisite for this course. And then for a period of time, you could take the two at the same time, but they were required. This was pre-BCS degree. So back in my day, you actually had to take both of the courses. So most students actually came into this course with an understanding of threads. But now, not only is 343 not required, but it's also not the prerequisite for this course. So we're actually going to start off talking about OS implementation details by talking about threads. But keep in mind there's this thing called processes, which is related, and we might mention it a little bit here. So I want to take you back in time, back to the 50s. And if you look at how programs ran in the 1950s, you started a program up and it ran. And when it was done running, somebody had to be sitting there to run the next program. Now, even if you had a batch processing style operating system, you still had to actually have that script that indicated when this job is done, please run this next job. And that might mean load the next job and then actually execute it. Now that works okay, except for a couple problems. One of the problems that you come up with is that it requires the machine to generally be maintained 24/7. And back in the 50s, this would have been the case anyways, because the machines cost so much money that you didn't want anything to happen to them. So they were generally maintained 24/7. But one of the big issues that came up is whenever a program wanted to do an I/O operation, let's say you wanted to write to disk. Now you might be thinking, oh, well, it's just like one box. It's like a CPU and it's got a disk attached right to it, and that should be fast, right? Except it's not. The CPU was physically on the other side of the room from the tape drives, which are the size of a fridge. And something that people don't take into consideration is when you issue that command, hey, write to the disk, write to the tape, it takes some time for that signal to travel along the wire from the CPU on the other side of the gymnasium to the refrigerator-sized tape drive. And once you get to the tape drive, it's a tape. It's like a VHS, except really big, fridge-sized. It's actually got to fast forward or rewind to the correct position in the tape before it can actually start doing the read or write. This takes time. What I'm saying is that every I/O operation, we're used to them taking, microseconds, milliseconds if you're using hard drives. But back in the day, these operations could have took minutes. They could have taken an hour. What is the CPU doing while the program is waiting for the I/O operation to complete? And the answer is absolutely nothing. And the problem is, when you have so few computing resources, you can't afford for your CPU to be idle for even 1 minute. Sorry about that. So what you wanted to do was you wanted to come up with a way to improve the utilization of the CPU and the resources in general. And they started out with this concept called multi-programming. And the idea was whenever there was a pause due to an I/O operation happening, well, since that program was waiting for the I/O operation to complete, why don't we run a different program and let it make some progress? Multi-programming. So when one program does an I/O operation, we let another program run some instructions. We are improving the utilization of the CPU. Now, this did work to improve the utilization of the CPU, and it kind of let several programs kind of slowly make progress at the same time, but there was never a guarantee. And one of the reasons why there's never a guarantee is not every program makes an I/O operation, or some programs simply don't make that many I/O operations. So it doesn't really, it doesn't always work that way. So then people started to think to themselves, wouldn't it be great if we could find some way of sharing the CPU so it looks like all of the programs are making progress at the same time, so everybody thinks that their program is running, so you don't have to wait your turn so visibly. And that's kind of how concurrency ended up coming about. All right. If you are watching live on Twitch, can I have someone just send a message to the chat room so that I can make sure that I'm seeing the messages? Thanks. All right, great. Thank you, guys. So, Windows updates, I could say a lot about Windows updates screwing you over, but there we are. Okay, so we're now going to start the Threads module. And of course, this is posted on the course website. You can print it out if you want. There's no requirement. We are not selling them in the course reserves because why would we do that? I don't want you to have to spend any more money than you already do. All right, so we came up with the idea of concurrency primarily because we wanted to improve the utilization of our resources. But we also came to this realization that it would be really nice if multiple people could run programs at the same time, or at least with the illusion that they were running at the same time. Not to mention, at some point in the future, at some point in history, we realized we could have computers with multiple CPUs, and it would be really nice if we could take advantage of that. And so this concept of concurrency and multi-threading kind of came to be. So then we have to ask ourselves, what even is a thread? So a thread is just a sequence of instructions. So if you have never done any threaded programming, you still have technically used threads. Because every program has to have one thread, because a program has to have a sequence of instructions. If your program doesn't have a sequence of instructions, it's not a program, it's an empty file. So every program is at least one thread. Now, we can actually have programs with multiple threads. And there are a variety of reasons why we might do this. One of them is things like improving resource utilization. But we can also use multiple threads to do things like improve the performance of our program. So we can use multiple threads to increase our parallelism. Now the parallelism, if you only have one CPU that can run one thread at a time, you're not really going to see a lot of parallelism from a multi-threaded program. But, we've had multi-core CPUs since 2003, and prior to 2003, it wasn't uncommon for people to buy motherboards that actually had 2 physical CPU slots. I've had one. It's kind of fun. You get 2 CPUs, one on this side of your motherboard, one on this side of your motherboard. You run 2 things. But nowadays, we have these multi-core systems, and each of those cores can usually run multiple threads. So if you're on an Intel machine, each core is hyper-threaded. Hyper-threading lets you do 2 threads per core. So I have an i9. That means I can technically do 12 threads at a time. So multi-threading my program, giving it multiple sequence of instructions, would actually increase the parallelism. I could do multiple things technically at the same time, which improves performance. The other things you can do is responsiveness, and this is something that we would do in something like video games or UIs. We will have threads completely dedicated to the UI and handling UI events, and then any kind of slower loading tasks or computation tasks could be done in other threads to ensure that our UI remains responsive while we're doing underlying computations. You can do threading if you simply want to organize your code better. There's so many different reasons why you can do multi-threading. And what I wanted to do is actually show you a few different things about threads. So first off, let's go over here to my terminal. So first what I'm going to do is I'm going to show you how to create threads in OS 161. So we're actually going to do a fair bit of demos today with showing you different parts of the kernel for OS 161, but also showing you how to run some things and use GDB, but we'll get there in a few minutes. For now, I just want to talk about using threads in OS 161. Well, if you're going to use a thread, you need a way to create a sequence of instructions. Now, you know how to create one sequence of instructions. You write a program and you compile it. But what if I want that program to actually spawn multiple threads? So we're going to go into the kern directory, and we're going to show you one of the built-in tests to OS 161. So inside of kern, this is what you will see. You'll see a bunch of directories here, and we're going to go into test. And inside of test, these are some of the built-in kernel tests that you have access to make sure that your kernel is running correctly. We are interested in thread test. Now this code, by the way, OS 161 was actually developed by Harvard, and it's about 20 years old, but it is fairly well documented, which is nice. But just be warned that the head of each of the files has got all that disclaimer stuff. So we are actually going to go down to line 105, and this is in a function called run threads. And run threads is actually going to create new threads. And what you see here in this for loop, so we have this lovely little for loop here. And inside of the for loop, we have this function called thread fork. And what thread fork is going to do is create a new thread. Now, when you create a new thread, you have to tell it what instructions do you want it to execute. Now, what we're going to do to thread fork, and this is a very common thing with many libraries, is we're going to pass it a function pointer, because that is the address of a region of code, a sequence of instructions. So by passing it the address of a function, we are giving the thread a sequence of instructions to execute. So in thread fork here, depending on the type of thread test I'm running, I'm either going to do loud thread or quiet thread. And I want to look at loud thread. All right, so inside of loud thread, there's a bunch of stuff that you probably aren't familiar with. For example, at the bottom, you'll see this VTSEM. Just ignore that for now. Probably next week, we'll talk about what that is. But what I want to point out is for each thread that is created, we are going to print that thread's number, because we can pass arguments to the thread. Just like we could pass arguments to a program, we're passing arguments to the thread. And the argument that we pass to the thread is going to be its creation number. So we're going to create them in a specific order, and that's the number we're passing in. And so each thread is going to print its number 120 times. And we are going to create 8 threads, 0 through 7. So this is an example in OS 161 of how to actually create a thread and have it execute some instructions. So if we were to run the loud thread test, what kind of output could we expect? So I'm going to switch to another tab here. This is in the root directory. And what we're going to do is we are going to run OS 161 here. So remember, you have to run the simulator because this is a MIPS-based operating system. And I'm going to take a wild guess that I'm going to say is accurate. None of you are running on MIPS hardware. So we are going to run our kernel. Now I'm going to run the assignment 0 kernel here. So there we go. If you load up OS 161, you should see your own name here. I'm not going to check and see if it's your name. I don't really care, but do change your name. of your OS to something. You'll see all of the subsystems load. This is all of the different devices booting up, and then you'll be met with a menu. And if you hit the question mark here, you can see the different kinds of kernel options that you have. And to see all of the kernel tests that are available, you hit question mark T to give you the tests menu. Now, the test that we want is thread test 1. That's allowed thread, so that's TT1. So let's run TT1 and see what happens. Well, I'm going to wait on pushing enter. Let's think about, what do you expect this test to do? Many of you might be thinking, well, if I spawn the threads in the order 0, 1, 2, 3, 4, 5, 6, 7, and each thread is responsible for printing the numbers from its number from 120 times, well, since I spawned them in a specific order, I should see 120 zeros, 120 ones, followed by 122s, and so on and so forth. And I would understand why you would think that. And in fact, that is a possible output, but it's very unlikely. What you actually are going to see is the threads taking turn, because printing out to the screen is an I/O operation. And I/O operations take time. And the program can't continue, really, until the I/O operation has been issued, completed. And in order to actually make sure that we are utilizing our CPU, we're going to switch away and run a different thread while one is doing an I/O operation. So we're actually going to see the threads taking turns. And we'll dive more into that a little bit later, but let's just run it. So there's TT1. So you can see it starts out 0, 1, 2, 3, 4, 5, 6, 7. But in the very next execution, we have 0, 1, 3, 4, 5, 6, 7. What happened to thread 2? Well, a number of things could have happened to thread 2. Maybe thread 2's I/O operation took a little longer than normal. And so when it went into the pool of threads, when it was done, it goes into a pool of threads that are ready to run, but not yet running. When the operating system then decides to run a different thread, it has to choose from the waiting threads. Maybe it just didn't select 2. So if you look at this, eventually we get wildly out of order. But they all will actually print. And what's interesting is every time you run this, you'll get a completely different result. So this time I actually got, you can see here, we've got a few of them executing in order. Now, I've said a few things that you're probably not familiar with. So first off, I said the threads are waiting in a pool. Well, our MIP CPU, I only have it set up to run with one CPU, which means it can technically only execute the instructions from one thread at a time. So what happens to those 7 other threads that are trying to use the CPU? Well, they have to wait somewhere. And they are not waiting on any particular event to happen except for the CPU to become available. So they are waiting in what's known as a ready queue or a ready pool. And when the thread that is running either is forced to give up the CPU or voluntarily gives up the CPU, when that happens, we are going to choose another thread to run from the pool that's waiting. And you don't know how they're getting chosen. And you don't know how long each I/O operation is going to happen, because maybe something happened, maybe there was an excessive delay, things get out of order. The point I want to make here is you actually don't have any control over the order of thread execution. It can depend on what is running underneath, it can depend on hardware. There are just many, many different things that affect the order of thread execution. Hence why each time we run thread test 1, we get a slightly different result. Now, one thing I want to mention about OS 161 is make sure that you do not run tests back to back. Now, thread test 1 can actually be run back to back, but if you're working on assignment 1 already, and if you are, that's wonderful. You can't run those tests back to back because OS 161 does not have virtual memory correctly implemented. You're going to fix that on assignment 3. And when you actually call free, it does nothing. So free in OS 161, please do call free, because otherwise it's going to bite you in the ass on assignment 3. But for now, free does nothing. So no memory gets freeze, which means after each test, there's no memory left in the system. So a question on Stitch is there any particular methodology for choosing the next thread from the pool? Yes. So there are different scheduling algorithms, which we will talk about in a couple months. But very briefly, you can imagine it could be things like first in, first out. So a simple FIFO queue. You can also do things like priority-based scheduling, where each thread is assigned a priority or a weight, and you always choose the thread from the pool that has the highest priority or the largest weight. There are many different techniques for that. We will cover that another day. OS 161, by the way, uses what's known as round-robin scheduling, which is actually a FIFO queue with preemption, and we'll talk about preemption a bit later. All right, now let's talk a bit about where threads belong in the world. So you have all of these threads. What do they belong to? Well, the threads belong to the program. So each program is going to have its own threads. So what I'm going to do here, if my tablet will fire up. Yay, it did. Let's open up a notebook. And I'm going to bring this over here. There we go. So all of these threads that we have, they all belong to a program. And each program has its own threads. Now, when we're saying program, what we actually mean is a process. So now, a process is more than just its threads. So a process actually has a few different things. So a process has, I'm going to try to write neatly, an address space. And the address space, if you remember from CS136, contains the program code. It contains the heap and the stack. And of course, there's the globals and all of those things. For this course, we're actually going to simplify our address space to just 3 things. And we're not going to even call it the heap in this course. We're going to call it data. So in our course, we have code, data, stack. Okay, so each program has its own address space. How do the threads behave? Because each thread has its own sequence of instructions. Well, what we have in a process is what's known as a thread array. Typical way we draw threads is squiggly arrows. So this is my array of threads. And we draw them this way because each one of these threads is supposed to represent a sequence of instructions. So this here is my thread array. And then down here we have device, access, stuff. And we'll fill that in another day. So what I want to talk about, though, is how this thread array interacts with the address space. So each thread is a sequence of instructions, which would probably make you believe that each thread must have its own address space, except that's simply not the case. Threads belong to the process. The process has a singular address space, which means that all of the threads of a process are sharing that singular address space. So all of these threads have shared access to the code segment. They all share access to the code segment. And that kind of makes sense if you think about how we created a thread. We created a thread by passing it the address of a function, which is the address of a sequence of instructions. And that address would have been part of the code segment of the process's address space. So all of the threads of a process have shared access to the address space. All of their sequence of instructions are going to simply be start at this address in the code segment. All of the threads also have shared access to the data segment, which is the heap. So all threads share access to the code and they share access to the heap. So you can actually use that to have communication between threads. So if you want two threads to work on something together or talk to each other, you put it in the heap because they can all see that. The exception to this is actually going to be the stack. Threads do not share stacks. And the reason for threads not sharing a stack, I mean, it's not that they couldn't, it's just that would be an implementation nightmare. But one of the primary reasons why you don't want threads to share a stack is because each thread is going to be doing its own sequence of instructions. So the local variables for a thread should be for that thread only. And that sequence of function calls pertain to that thread only. And we don't want, thread 507's sequence of function calls in our stack. That doesn't make sense. We keep them separate. And what that ends up looking like is instead of having one stack down here, we end up actually having a bunch. And we'll look at that again in a minute. So there you go, the connection between processes and threads here. All right, let's get my mouse back. All right. So what I really want to emphasize here is that all threads have shared access to the code segment and all threads have shared access to the heap and global variables. What they don't share is their stacks. So stack frames and local variables are completely private to the thread. Now, let's talk about the API for OS 161. You've already seen the thread fork function, and we use that to create a new thread. It has 5 arguments. The first one is the name of the thread. Now, you might be thinking to yourself that using the name of a thread has to be unique, but it doesn't. There's no guarantees that thread names are unique. And that's important to know because that means that you should never use the name of the thread to identify it. If you need to identify a thread uniquely, inside of the operating system, a thread is a struct, which means it has an address, and that should be how you uniquely identify it. The purpose for having a name for your thread is really for debugging. The other thing we have is the process. This is which process does this thread belong to. And then our third argument is the pointer. Make sure if you're using thread fork that you follow this signature exactly. If your signature to the thread fork function doesn't match, this won't work. So our function pointer here takes 2 arguments, and that is a void pointer and an unsigned long. So you have 2 arguments that you can use to pass data into the new thread. And then the last 2 arguments to thread fork are the values you are passing forward to your new thread. And that is going to create a brand new thread when you call thread fork. Now, what does that actually look like? So let's go back over here to our kernel. And let's leave this directory here. And let's go into include. Now, this operating system is actually fairly well designed. And most of the include files can be found indeed in current include. So here they are. And we're going to open up thread, helps if I can spell, thread.h. And here we are. This is the thread structure. So a thread, you can see here, we have a name. And don't worry about this wait channel name bit here. Then we have a variable we use to keep track of the state. We have information about the address of the thread stack. We have information about which process it belongs to. We can keep track of what CPU this thread is running on. And then there's a bunch of other things that we're not going to worry about for now. But when you call thread fork, what you're doing is you are actually creating a structure of this kind. And then what the operating system is going to do is it's going to take that thread and it's going to say, all right, this thread is now ready to run. and it's going to put it into that ready pool of other threads that are ready to run, where it will sit and wait for the kernel to actually choose it and actually move it to the CPU. So that is our thread structure that is created on thread fork. Now, there are other API functions for threads that you will actually see and possibly make use of. There's one called thread exit. And thread exit is not necessarily required, because if you pass to thread fork a function, which is what you do to say, hey, here's your sequence of instructions, when you return from that function, the thread will terminate. But let's suppose you want to terminate the thread prematurely. Let's suppose you've got some kind of deep recursion and you don't want to have to pop all of those things off of the stack to finally kill the thread. You want to kill it right now. Then you call thread exit and it will terminate the calling thread. Now, another function which isn't terribly common to use is called thread yield. And what thread yield does is it is saying, I'm voluntarily giving up the CPU. Now, it's not a guarantee. So if you call thread yield, thinking to yourself, I'm going to use thread yield to give another thread an opportunity to run, there is a probability that no other threads will run and you will keep running even though you have technically requested to yield the CPU. And that actually comes down to the scheduling and how many other threads there are. So there is a probability that you say, hey, I'm volunteering to give up the CPU, and you actually keep running. So keep that in mind if you're using, if you want to guarantee that you're giving up the CPU. Thread yield isn't the way to do it, because thread yield doesn't make the guarantee. Now you might be wondering then, what the hell is the point of thread yield? Actually, there are a few issues with synchronization where we could leave it to chance that the kernel will just evict the current thread from the CPU, or we could encourage the current thread to give up the CPU. So we want to, because probabilistically speaking, thread yield will succeed most of the time, especially on like the computer sitting in front of you. The computer sitting in front of you, if you call thread yield, it's probably going to work. On OS 161, yeah, maybe it won't work. By the way, if you hear the vacuum, that's probably because there was a spider in the basement. All right, so thread yield, it's not a guarantee. On a modern system, it almost always works. But on OS 161, not so much, because there's not really other threads running. And the scheduler is kind of simple. So we do use it in synchronization problems to try to encourage giving up the CPU. A place where actually thread yield is really common is something called cooperative concurrency, which we'll talk a little bit more about later. But effectively, it's an older style of concurrency that Windows and macOS used up until about 2000, where instead of rapidly switching between the threads involuntarily, the only way that you could switch between threads was if you blocked, if you terminated, or you voluntarily yielded. But again, we'll talk more about that later. So these are all of the functions that you have available to you. And if you've done threads before, you're probably looking for some kind of join command. OS 161 does not have join. The idea behind join, for those of you who've never seen it, is you want a thread to be able to wait for another thread to finish. While we don't have a thread API ability to do that, there are many other mechanisms by which that can be implemented. So we still technically have that ability. So question on Twitch is, will there be any point to us using thread yield in our assignments? I have never used yield in this course. I almost never use yield. So I have used it in some of your course slides to improve the performance of certain algorithms related to synchronization, but for A1, A2A, A2B, and A3, I did not use yield at all, nor did I really see a reason to use yield. On a personal note, I can't think of a time where I said to myself, I need yield. I just haven't needed it. If I need something to give up the CPU, I usually use sleep, actually. And the reason why I would normally give up the CPU using sleep is if I'm running a ray tracer, which is a computationally intensive program, it has a habit of overheating the CPU. And so I want to cool the CPU down by causing the thread to pause for a period of time. So yield won't do that, but sleep will. Sleep is a guarantee. I tell it sleep for a minute. It sleeps for a minute means that program stops running for 1 minute, which means the CPU isn't doing that intensive work anymore. Now, another question on Twitch is, what do you mean by giving up the CPU? Well, what I mean is when a thread is running on the CPU, it kind of owns the CPU. When you give up the CPU, it means you stop running on that CPU. You stop executing instructions. All right. Now, I really recommend you get some experience with threads. If your only experience really with low-level programming has been CS136 and CS246, threads are probably not something that you've encountered, but in the modern programming world, threads are absolutely a critical thing to know because we have multi-threaded CPUs. They support many threads at the same time. People do GPU programming. That's general purpose programming for your graphics card. It means let's take a regular program and instead of running it on our CPU, let's run it on our graphics card. And if you're wondering why the hell would we actually do that, it's because while our lovely i9s might have 6 cores, my NVIDIA card in the basement on my research machine, which is currently toasted, has thousands of cores, which means it can run thousands of threads at once instead of just 12. And if you're sitting there wondering, then why don't we use GPUs for everything? GPUs lack branch prediction, which is a big problem. And they also require the threads to all execute in what's known as lockstep, which means all threads have to be executing the same instruction at the same time. Kind of means that there's only one instruction pointer, one program counter for all things. We're not going to get into that. So the point I'm trying to make is threads is a really big topic in today's programming world, whether you're doing asynchronous web development. Hey, guess what async means? Or even synchronous web development means that there's probably multiple threads or multiple users you need to think about, or multiple events going on at the same time. That means threads. So I highly recommend to you that you get some experience using threads inside OS 161 and outside of OS 161. I really recommend you take 343. It's a shame that course isn't required anymore, but I think it's really valuable, especially for future development. So, program that you can write to play around with threads in OS 161 is called a fork bomb. It's one of my favorite kinds of programs. Now, I wrote one, but I didn't write it in for OS 161. I actually wrote it for my computer here. I'm not going to run it, though. I made the mistake last term of running this while live streaming, and it took the computer down. Which is what it's supposed to do, but I didn't think it would happen that fast. So what a fork bomb is you want to overwhelm the system with threads because each thread is going to take more memory. So you're going to be consuming a lot of resources and you want to be creating threads at a rate faster than the threads are terminating. So try to create a fork bomb in OS 161 that mimics what I'm about to do here. So I'm going to open up fbomb.cpp. Yes, it's in C++. So in this fork bomb, so I want you to try running the fork bomb in OS 161. Try adding a kernel test that is a fork bomb, a thread fork bomb. And then try using the pthreads library. So pthreads, as known as POSIX threads, is a cross-platform threading library that's super, super common. And I highly recommend that you get some experience with it. So what I have here is I've written a thread fork bomb in pthread. So I have my main function, and it doesn't really do much. It just calls the fbomb function, and then it just, this thread that called fbomb is just going to keep running. So what we have here then is in my fork bomb is, see, I thought after like a million threads that would, the program would die gracefully and it wouldn't wreck my computer. But it did. So what I'm going to do is I'm going to create 3 new threads from this thread, and each of my new threads is going to run this function. So you get an exponential number of threads being created, which is kind of nuts. Now I see someone on Twitch has commented that there's already a fork bomb function in OS 161. And yes, you are correct, but you're also not correct. The fork bomb that you are looking at is not a thread fork bomb. That is a process fork bomb. And that is a slightly different kind of fork bomb. So this fork bomb that I have here is one program creating an exponential number of threads for itself. So all of these threads will belong to this F-bomb program. The fork bomb that you see in user test bin fork bomb is a process fork bomb, and it's going to create an exponential number of processes. The difference between these two kinds of fork bombs is if you were to look at your task manager or top, for a thread fork bomb, you would only see one process, but that one process would have an exponential number of threads. And it would be consuming a significant amount of resources. So the advantage to that kind of fork bomb is that it's a little bit harder to see it in the task manager, but it's really easy to kill it because you see, oh wait, that program, its resource consumption keeps going up, you terminate it. The problem with a process fork bomb, it's easy to detect because you open up top and you'll see like a billion processes by the same name. Good luck killing that though, because in order to kill it, you have to kill all of them. And since they are spawning at a rate faster than you can actually kill them, all you can do is reset your computer. And if you want to be a real jerk about it, you write one of these process fork bombs and you make it so that when Windows loads, it's part of the boot process. And you end up with a very interesting, very simple kind of denial of service attack on a Windows machine. Sorry, you see me laughing about this because I've done it. When I was in high school, I was bored. Anyways. All right, so there's an example of using pthreads for you. Now, let's suppose you're super lazy, and I don't know about you, but I tend to be a little bit on the lazy side. And you want to do threads, but you want to, I don't want to have to think about creating the threads, and I don't want to have to worry about all this nonsense. There is another really common cross-platform thread library known as OpenMP, which we actually mentioned in the slides here. See? OpenMP. So we talked about pthreads, and then there's OpenMP. I love OpenMP because it's so easy to use and it's so lazy. And it can do all the regular threading things, but I want to show you what OpenMP looks like. So I have another program here. Here we go. And this is actually using OpenMP instead of pthreads. So you'll notice that I don't explicitly create any threads. In fact, you don't see any thread creates, you don't see any pthreads create, you don't see anything. But you do see this extra command here. So in this particular example here of creating multiple threads, what I have is I'm pretending that I'm trying to perform some operation on a very large image. Considering I'm in graphics, I do operations on images all the time. Now, each pixel of my image, I represent my image as a two-dimensional array, each pixel of my image I'm going to manipulate independently. And this is a classic example of where multiple threads can really improve your performance, especially if you have a multi-core CPU. So I almost want to create one thread per row of the image, or maybe one thread per pixel. It really depends on what you're doing. Now that would be a lot of calls to pthreads create, so I just don't want to do that. So what I'm going to do is I'm going to let OpenMP handle it for me. So for loop, no changes there. And then what I do is just before my for loop, I put pragma OMP parallel for. And OMP handles it for me. So what OpenMP is going to do is it is going to actually create one thread for each index of the loop. So it's going to figure out how many it's going to figure out how many times the loop will run, and it will actually like create threads for each of them, or create some number of threads, and you don't have to worry about it. It just handles it. Now, it also, if you wanted to create a specific number of threads, you can do that in OpenMP. And if you want to do synchronization, you can do that in OpenMP as well. But this is a really lazy, really easy way to get parallelism or multiple threads out of a program. Now, so those are the different libraries that you have. Now, we've told you that threads can improve the performance, but we haven't proved it to you. So what I want to do now is just give you a very quick example of what it's like running a program with threads versus without. So I've already compiled these, and I'm going to run them with the time command. So this is comparing threads to no threads, and it's just doing some processing on each part of an image. So I'm going to run no threads first. And let's see how long it takes. Time, by the way, is a Unix command that will actually show you how long a program takes to run in both real time and kernel time as well. Oh goodness, this is probably slower than I remember. There we go. So it took about 22 seconds. Okay, so now I'm going to run the exact same thing, except it's using OpenMP to parallelize the for loop by creating some threads. Oh. Oh, I have been foiled. That's so annoying. Let's see if this works. You know what? We'll do that experiment later. If you're wondering what the hell is running, or what's going on here. Little known thing about Apple computers is when you install Xcode, you think you'll get GCC. And everybody thinks to themselves, oh, look, I have GCC on my Mac. Except, if you run GCC-version, what you really realize is that Apple has renamed Clang to be GCC. So it's not actually the GCC compiler, it's actually Clang. So you actually have to install a proper version of GCC, which sucks. Let's see, we'll try one more time. I can never remember the flag for this. I'm really bad at remembering flags. Yeah, we'll do it another day. Sorry about that. All right, so there was a question here about what is the difference between real time and kernel time. So real time is how much time it takes from a human perspective. And if we actually scroll up here, you'll see that there's the real time. So this is how much time things took from our perspective. User is how much time the user program that we just ran, the process, actually took to run. And then sys is how much of that time that we experienced was spent doing other things other than running our own program, i.e. running kernel code. And that was 0.308 seconds. And if you're wondering, does user plus sys equal real? Not necessarily. Yeah. By the way, that little plug about GCC on Apple, if you are trying to get OS 161 running natively on your computer, you actually have to download and install proper GCC. And make sure that you change all of the make files such that they are pointing to proper GCC and not the Clang-based GCC. The Clang will compile some of the tools, but it will not compile all of them. And in fact, I think it's GDB that Clang can't do. So yeah, a warning. So the other question here is the definition of a process. So a process is the program's execution environment. It is the address space, the array of threads, and a bunch of other resources that are used for the program to run, such as keeping track of what files are open for that particular program. All right. So, and another question, the join function. So join, let's suppose you create a bunch of threads to do a task. So map, you know map from CS135, where you apply the same function to each of the elements of the list. Well, maybe you are applying a function to, let's say you want to count how many times the word the appears in every Wikipedia article. So you create a thread for each Wikipedia article to count how many times the word the occurs in it. And then you want to know at the end, how many times does the occur on Wikipedia? Well, you have to reduce the results of the map collected into one final result, which means you need the original thread to wait for all of the map threads to complete. The join function is a way to let one thread wait for another thread to terminate. We do not have join in OS 161, but we can still get that behavior using other tools. It's very useful, by the way. All right. So we've talked a lot about this already, but just to review, sequential program execution. I know CS251 was probably a long time ago for some of you, and we all know how it works. The very second you put your pencil down at the end of the final exam, the course disappears from your mind. So our address space, as I previously mentioned, we have code, data, and stack. The layout of this address space we're not going to discuss today, but we will discuss at a later date as to why it's laid out this way. Then we have a CPU with some registers. We have a program counter that points to the address of some instruction in the code segment. And then we have a bunch of other registers, and some of them point to things like stacks and so on. And then the CPU, it doesn't know about the threads. It just knows my program counter points here. I'm going to fetch the instruction that it points to. I'm going to decode it, execute, increment the PC, and continue about my business. Now, a couple other things to remind you of when it comes to just regular program execution. We are using a MIPS CPU, so it's very similar to what you did in 241 and 251, unless you're from the new ARM period. However, I will say that the ARM architecture is a RISC architecture, just like MIPS, so they're quite similar. And for those of you who are shaking your head like, oh no, not MIPS again. Why do they keep showing us this educational made-up thing? MIPS is not an educational made-up thing. MIPS is actually a real CPU, a real piece of hardware. And in fact, I have had many co-op jobs where I've actually done development for MIPS hardware. For example, if you're curious as to know where MIPS hardware lives, so we're using a simulated MIPS R3000. If you had a PlayStation 1, you had a MIPS R3000 because it was the main CPU. If you had a PlayStation 2, you had one as well because one of the secondary processors was actually the MIPS, a MIPS processor. So that's kind of neat, eh? MIPS is real. MIPS is everywhere. Not so much anymore, but it's quite a popular architecture. All right, so our MIPS architecture that we are using is the R3000. It has 32 registers. 0 is 0. 31 is the return address. We've got a stack pointer and a frame pointer and a global pointer. We're not going to worry about those. Now, we have a convention in OS 161 for how we use these registers. This is a convention that is agreed upon by both the operating system and the compiler. These two things, the operating system and the compiler, are very tightly integrated together. They have to agree upon these conventions and obey them, because if one does it and the other one doesn't, things are not going to work. So we have some very special conventions. Registers 4 through 7, which correspond to what we are naming in OS 161, A0 to A3, those are for the arguments to functions. Then we use V0 and V1, which are registers 2 and 3 for return values. Now you might be wondering, why do I have two returns? We need two returns, as we will see in processes, because sometimes we need to return an error code. And how do you differentiate between an error code and a correct result? And you might be thinking, well, just have the error codes negative. Well, what if I'm adding two negative numbers together? The answer isn't an error code, it's a negative number. So we actually need two return registers, one to indicate success or failure, so we know how to interpret the other register, which contains either the result or the error code. All right, then we have the S and T registers, which are general purpose registers for the functions. And we have divided them into caller save and callee save. Caller save means it's your responsibility as the function to save and restore the values of those registers before you use them. The callee save registers means that it is the responsibility of the called function to save and restore the values of those registers before and after use. So to show you a brief example of this, if you've got function A, function B, and function C here, function A can use the S registers without saving them, but function B, if it wants to use the callee save registers, it has to save them before it can use them. And this is, again, a convention that's agreed upon between the operating system and the compiler. They are always going to do this. So the compiler will make sure that the callee registers are saved and restored by the called function, and the caller save registers are saved and restored for the caller. All right. Now, again, one last thing before I go into our OS 161 demo again, just to kind of rehash this idea that all of the threads are sharing, the threads of a process share an address space. So we have a process address space, we have one code segment for the whole process, one data segment for the whole process, and then each thread is going to have its own stack. Now, this diagram here might make you believe that there are multiple CPUs and the CPU then has to have multiple sets of registers, one for each thread, but that doesn't actually make sense. And the reason for that is because the CPU doesn't know how many threads there's going to be, and registers actually take up a lot of space, physical space on the actual physical chip, and we want to minimize the size of the CPU. So the CPU only has one set of registers, but only one thread can run at a time. So any other thread is going to store its register values on its stack until it's its turn to run, and then we will restore the register values to the actual CPU at that time. So threads are going to have their own stacks where they keep their own local variables and their own register values when they're not actually running. So we see, aren't the location of these two things switched? No, what we're saying here is that before function A, there was other things. The other thing is that the stack actually lives at the end of the memory, at the end of the address space. So a lot of people think you've got code, data, and then the stack right here, but you don't. We actually put a lot of space between the heap and the stack, and the reason we do that is so that they can grow. So the stack's going to grow towards 0, and the heap's going to grow towards the end, and we want them a maximum distance apart. Now, that being said, it kind of gives you the illusion that they can grow to an arbitrary size and possibly overlap each other. And what do you do when you have multiple thread stacks? The answer is there is actually a maximum stack size. And this is true in OS 161, where the maximum stack size for a user program is 48 kilobytes, and the maximum stack size for the kernel is 4 kilobytes. And then this is also true for macOS and Windows and Linux. There is a maximum stack size, and depending on how you run your program, it's like 1 or 2 megs, and that's it. That's all you get. Now, you can't change it, but the stack size is actually quite small. And if you want some proof of this, here's a fun program you can write. So open up, if you're running Windows, Visual Studio. If you're on Linux, open up VI. And try to create a really, really large thing on the stack. So try to create like a 5 or 10 megabyte array on the stack. And if you're wondering how do you do that, you're going to need to make a struct. so that the struct actually contains lots of things, and then create an array on the stack of really large structs. And what you'll see is that it doesn't work because there is a limit to the stack size. It's kind of fun. Fun experiment to do. All right, so there we have an introduction to what threads are and where they come from and why we might use them. We've seen how to use pthreads, we've seen how to use OpenMP, we've seen how to use OS 161's threading library, and we've done a brief review of program execution for single thread versus multi-thread. So what I'd like to do now is go back to my terminal here, and I'd like to give you, just in these last few minutes here, an example of using GDB. So first off, in order to run and debug your operating system, you are going to need 2 terminals. Now, in your first terminal, this is where you are actually going to run the operating system. And make sure that when you're doing this, the 2 terminals must be on the same computer. So when you're SSHing into the school machine, make sure that you don't just do SSH linux.student.cs. Actually choose a machine name, which you can get off the CSCF website, and log into that specific machine. Because if you're not on the same machine, this won't work. So we're going to run sys161, and we're going to use a flag W to wait for a compiler connection. And you can see here, it says waiting for debugger connection. And now I'm going to go over to my other terminal, and I'm going to start the debugger. Now make sure that you have your paths all set up. So you're going to use CS350 GDB. And when you do this, it's very tempting just to type CS350 GDB. You actually have to specify which program you want to run. So I want to run it on kernel 0. Okay, now if we go back over here, you'll realize nothing's happened. And that's because we haven't connected GDB to the OS. So to connect GDB to the OS, we need to run a couple commands. And I recommend that you put this in like the GDB init. So first, we're going to tell it where to find things. So there we go. And now I'm going to actually do the connection. So the connection is to do this target remote Unix. And all of these instructions, by the way, are actually on the course website. So there we go. I am now, if we go over to OS 161, you can see that it's actually registered that the debugger has connected to it. But nothing's happened because we haven't actually booted the program yet. Now, I'm going to actually, I recommend you put the breakpoints in before you boot OS 161. Otherwise, you won't have that pause where because the OS will be running and GDB won't have any way to stop. So I'm actually going to put a breakpoint in thread test 1, and I'm going to create a breakpoint. If you're not familiar with breakpoint, when you reach this, you are going to stop executing, and it will let you explore the stack and the values of the variables. So in GDB, you can use the letter B to create a breakpoint. And then there are several ways that you can do it. You can say B and then the name of the function you want to break on. But I find that very imprecise, and I like to break at a very specific point in a very specific file. So to do that, I'm going to do B threadtest.c. So that's the file I want to put the breakpoint in, and then colon the line number, and I'm going to put it on line number 64. And when you do that, you can see breakpoint 1 is at this address in this file at line 64. Now you might be wondering, what is this address? That's the program counter address. That is the address of that line of code in the actual compiled code. And if you're wondering, why is it at this huge address? We'll explain that in virtual memory. Okay, so I have a breakpoint now. I'm ready to run my program. So I am actually going to run the program, hit C for continue. And now you will see over here, OS 161 has now booted. And now I'm going to run thread test 1, which is TT1. So I run thread test 1 and I push enter and you'll see it immediately pauses. And that's because if we go back over to our other terminal, we have reached the breakpoint. Now it often happens that you don't remember where your breakpoint was. So what you can do is type list, and list will actually show you a few lines before and a few lines after your code where your breakpoint is, so you can actually recall what the hell is this breakpoint, where is it? All right, so a quick question here on Twitch. I've shown you how to make breakpoints, so I'm not going to answer that again. The other question is there a limit to the thread stack size? What if the thread 1 needs more stack space, but it hits thread 2 stack? Yes, there is a thread stack size limit. It is operating system dependent. In OS 161, the kernel only permits its stacks to be 4 kilobytes and the user programs get 48 kilobytes. I'm glossing over a lot of details there. We will get there when we talk about processes. But yes, there is a physical limit. And that is also true of every other operating system, but they typically have much larger stack size limits. All right, so back to debugging here then. So now that I have broken the program execution and I've seen where my breakpoint is by typing list, I can now actually explore what is going on in this program. So one thing that's very useful is sometimes a function is running and you don't know why that function is running because it shouldn't be. So you need to know who called that function. You need to see the stack. So you type BT for backtrace. And it will show you the contents of the stack. So you can see that loud thread was called by thread startup. And you see here that there's nothing else because this is a brand new thread. And that's all that's done. If this was a much deeper function, you would see, more stack frames on this stack. So now I know thread startup started this. So BT, very, very useful. It tells us what was the chain of function calls that led to this breakpoint being hit. And so if a mystery function gets called, you can figure out who called it and who called that and who called that. Something else that's really, really useful is the ability to actually explore the values in the variables. So we can, for example, print the value of CH. There we go. So you can use print to actually print the value of your variables. Now, what if I want to explore my thread structure? So there is a global thread structure known as curthread. It's just a pointer to whatever thread is currently executing. So I can print curthread, and it will show me what thread is currently running because it's a pointer. But wait a minute, it's a pointer, so all it's going to give me an address. Well, here's an interesting thing about GDB. GDB understands pointer arithmetic. So we can actually say, not show me the address of the current thread, show me the value of the current thread by dereferencing. And there you go. And it's going to spit out the contents of the curthread structure. So, curthread is a pointer, and this is what it's pointing to. So we've got the name of the thread, we've got the state it is in, it's running, and we've got other information about where its stack is and so on and so forth. So very briefly, you've seen how to start OS 161 and connect the debugger. You can see how to place a breakpoint, how to continue execution. We've shown you how to display the stack, how to list the code around it, and also how to display the contents of variables. So with that, I do believe that you have enough now to actually get started with running OS 161. And on that note, if you are one of these individuals that debugs by printfs, it's not going to work for you this term. You have to use GDB some of the time in this course to debug certain things. Printfs are going to control the order of execution and hide bugs. So what's going to happen is you get a bug, you put in some printfs to find the bug, but when you put the printfs in, there's no bug. So you take the printfs back out and the bug's back. Oops. You're going to have to use GDB here. And it's not that you can't use printfs for some debugging purposes. They are still useful with helping you identify where in the code you are in order to where should I put the breakpoint. It's just that there are some things you can't effectively debug without GDB for this course. So please take a few minutes to actually learn how to use GDB. We have a tutorial on the course website. I recommend you go through it. All right, so with that, in our next episode, we are actually going to continue our discussion of threads. And in particular, we're going to discuss how do you actually implement concurrency or multi-threading? How do we share the CPU between thousands of threads? So I will leave that there, and we will see you next week.
You've heard all about the many fabled wonders of the information superhighway. With Windows 95, it's easy to get on it. Start connecting. Start Windows 95.